As we begin our unit on area, we need to look at the concept of area. When we measure lines, we measure a distance from point A to point B. That's a linear unit. That's measuring one dimension, and the exponent on the unit is a 1. Typically, it's not written, it's implied. When we measure area, we measure 2 dimensions, usually thought of as length and width. 2 dimensions are noted by the exponent of 2. Any closed region can be broken into a number of squares. Those squares, if 1 unit by 1 unit, can be counted up to estimate the area. The areas of rectangles and squares can be found by multiplying the base times the height. In a square, considering that the base and height are equal, you could simply take the sides squared. Every closed region has an area. If 2 closed figures are congruent, then their areas are equal. Let's take a look at this example. Here we have a rectangle with a dimension of 5 on one side and a diagonal of 13. I hope you recognize that as the Pythagorean triple, such that the other side would be 12. Then 5 times 12 is 60. Here, we're not given one of the dimensions, but we are given a dimension of 5. We're also told the area is 20. So 5 times x equals 20. The unknown dimension is 4. If 2 closed regions intersect only along a common boundary, then the area of their union is equal to the area of the sum of their individual regions. What that means is if you have an oddly shaped figure like this, you can break it into shapes that you know. Here your book is breaking it into 2. If I were doing this, I would break it into 3, a triangle and 2 trapezoids. We are not going to be studying calculus in geometry, but I wanted to talk to you for a moment about why area is so important. Calculus deals with basically 2 concepts: the rate of change, or the speed of something, and area. In calculus, you'll do a lot of areas of oddly shaped regions, such as this curve here, bounded by A and B and the x-axis. In theory, what you can do is break this into a bunch of little rectangles. And that's why we have figures like this. There are 2 ways you could figure out the area of the shaded region, as shown here. You could actually add on parts where this area is 4 and this area is 10, and then take the area of the whole big figure, which is 96, subtract off the 14, and you'd get the 82. You can either make one big rectangle and subtract off those parts, or you could cut that shape into a bunch of little rectangles. If you do that, don't go in a bunch of different directions. Just keep it as simple as possible. Some examples. If I make this into one big rectangle, then I have 6 plus 5 plus 7 is 18 from end to end. Since I don't have a calculator, I'm going to use place value. And when I distribute, 10 times 10 is 100. 10 times 8 is 80. Then 4 times 10 is 40. And then 4 times 8 is 32. That equals 120, 220, 252. Then I need to subtract off this part. I'm going to repeat that method here by examining one larger rectangle. Since this length here is 4, the 8 plus the 4 gives me 12. Since only this part here is 5, and this part here is 3, this height is a total of 8. 8 times 12 is 96. Then 3 times 2 is 6. 3 times 4 is 12. Subtract the 18, and we get 78. Looking at part C here, the distance from the y-axis to this point here is 6. From the y-axis to the left is 4. The total distance horizontally is 10. Using the same concept, the distance from the x-axis to this point is 5. From the x-axis down to our first point is 3. So the total height is 8. 8 times 10 is 80. The next set of examples asks us to find the area of each rectangle. So here we know all rectangles have a right angle. We can draw the diagonal and then we have a right triangle. This is a Pythagorean triple. So 8 times 15 is 120. Here the perimeter is 40, one side is 6. So then 2x plus 12 equals 40. So 2x equals 28, x equals 14. Then to find the area, we need to take 6 times 14, and that is 84. Zooming in just a little bit here. Find the area of a square whose side is 12. 12 squared is 144. Find the area of a square whose diagonal is 10. I'm going to need a little more room for this. So the diagonal is 10, and that's a right angle. Remember, if the sides are congruent, then the angles across from those sides are congruent. So here we have a 45, 45, 90 triangle whose sides are x, x, x root 2, and across from the right angle is x root 2. If x square root 2 equals 10, divide both sides by the square root of 2 and rationalize that denominator. We get x equals 5 root 2. We were asked to find the area of that. So 25 times 2 is 50. Find the side of a square whose area is 49. Well, the square root of 49 is 7. Find the area of a square whose perimeter is 36. If the perimeter is 36, then 36 divided by 4 will give us the length of the side. The side is then 9. So the area is 9 squared, or 81. The diagonal of a rectangle is root 29. The base is 2. We need to find the other side. Here I'm going to use the Pythagorean theorem. X squared plus 2 squared equals the square root of 29 squared. then the area is 5 times 2, or 10. The semi-perimeter, semi means half. Therefore, the semi-perimeter is 5 plus 2, or 7. The sides of a rectangle are in a ratio of 3 to 5. The area is 135. So I'm going to set that up. Remember, whenever we see the word ratio in a word problem like this, we should think x. So 3x and 5x. So 3x times 5x equals 135. 15x squared equals 135. 135 divided by 15 is 9. The square root of x squared is plus or minus 3. However, remember we're dealing with lengths. If I replaced the negative 3 for x here, I would get a length of negative 15. So that solution doesn't work. We only want the positive 3. So the dimensions of the rectangle are now 15 by 9 meters. So here I have W, X, Y, and Z. So if each has an area of 100, 100 divided by 20 is 5. 100 divided by 10 is 10. 100 divided by 4 is 25. And 100 divided by 8 is 12.5. The perimeter then would be 50, 40, 25. 25 is 50, plus 4 and 4 is 58. And if this is 8, that's 8. 12.5. 12.5 is 25 plus 16 is 41. So find the missing dimension of each. What length of fencing is needed to go around each? 100 feet, or whatever the unit is. Which figure has the shortest perimeter? This, gentleman, is extremely important. What do you think must be true about the rectangle that encloses the maximum possible area with the shortest possible perimeter? I used Excel to delve into this a little deeper. If my perimeter is restricted to be 100, I considered whole unit lengths and widths, not fractional, and calculated the area. If I'm looking to maximize the area, we have length times width, 2 dimensions. Remember when I said the exponent on 2 dimensions is a 2? The area continues to increase until we get to here. Look at those dimensions. What do we call this point? That moment when the graph changes directions. Let's look at another example. Here I've restricted the perimeter to 80. Again, the area increases until there. Isn't that the vertex? And if I restrict the perimeter to 20, the vertex is at 5. So in all cases that we've examined, these multiple examples, what do you think must be true about a rectangle that encloses the maximum possible area with the shortest possible perimeter? It's a square, a regular polygon.